Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Welcome to Thermal Diffusional Process class with me, Hanif Prastiawan. And in this video, we are going to discuss an example on the single effect evaporator calculation. So in this example, we are going to calculate the heat transfer area for a single effect evaporator, or I can simplify it by using SEV in here. For an SEV that is used to concentrate a salt solution, and here is the example. A 1.5% weight aqueous salt solution is concentrated to 4% weight in an SEV. The feed rate to the evaporator is 7,500 kg per hour, and the feed is at 85 degrees C. The evaporator operates at 1 bar. Saturated steam at 170 kPa heats the evaporating solution. What heat transfer area is required if the heat transfer coefficient is 2800 watt per meter square Kelvin? So actually, for heat transfer equipment such as heat exchanger, evaporator, condenser, and etc., the price of this equipment is really dependent on the transfer area. The larger of the transfer area, then the price will be higher compared to an equipment of transfer area, an equipment with a lower transfer area. So how to solve this sample? Then we have to draw it first about how the SEV diagram. Let's draw the SEV diagram first. So we have this one is the evaporator, let's say like that, and then maybe I will change it into black. This one is the evaporator, and this one is the transfer area, the contact between the evaporating liquid with the steam. And this one will have a line of steam, and then this one is the outlet of the steam, and we have the feed itself. Maybe in here, this one is the feed. At the top we have the vapor, and at the bottom we have the liquid exit the evaporator. Well, for the feed itself, it has a fraction of the solid, and it also has the temperature of the feed. For the vapor, in here we have a temperature exit evaporator. Let's say in here is the evaporator, and then this one is the liquid inside the evaporator. So the contact between evaporating liquid with the steam is not contacted directly. So the steam go through, usually it depends on the type of the evaporator. Is it a tube? Usually the steam is flowing through a tube. And this one in here, for the liquid exit, we have the vapor fraction of the solid exit from the bottom. We have XL in here, and we also have the temperature of the evaporator. So in here we are assuming that the temperature inside the evaporator is the same with the outlet temperature at the vapor and at the liquid. While for the steam itself, it has a saturated temperature, since we have saturated steam in here. course, and the condensate, we also have the same amount of the steam exiting the evaporator. Okay, is it clear? Hopefully it's clear. And let's continue. Let's write down everything that we know from this sample. The aqueous salt solution, it means that the fraction of the solid in here is 1.5%, while the feed rate of the feed rate is 7,500. So the F is 7,500 kilogram per hour. The feed itself enter at 85 degrees C, and the saturated steam has a temperature of 170. Oh, sorry, not temperature. What we know in here is the pressure. The temperature, the pressure, and the fraction of the solid and the liquid is 4%. So what we can assume in here, the first one, we can assume that this process, or inside the evaporator, the liquid is well mixed. Any liquid gas, that's why in here the temperature is assumed to be the same. The temperature at the outlet of vapor and liquid is the same with the temperature at inside the evaporator. So after the feed is contacted with the steam, of course there will be a transfer of the heat transfer inside, and the temperature will be changed. It won't be the same like with the inlet again, but it will increase because it is heated with the saturated steam. And the second one, since we are dealing with the heat transfer, means that we also need to calculate the delta H of vaporization. Delta H vaporization of a mixture, for the feed is usually a mixture, right? In here, for example, we have a mixture of salt. So on the heat of vaporization, we can assume it by using heat vaporization of water, since maybe there will be a little bit change, or not, it won't be accurate, but for this example I think it's okay. Actually, you can find the delta H of vaporization for a certain mixture from the graph. You can find it in a reference book or any website or any journal if you can find it. So we are assuming the delta H vaporization is assumed to be the same with delta H of water. And for the third assumption, there won't be any heat enter the evaporation instead of heat from the steam. So heat of mixing is negligible, yeah, assumed to be zero. And the last assumption, no boiling rise point. Logically, when you are having a solution with a certain amount of solid, and then the solution or the solvent is evaporated, then of course the temperature of the solution inside the evaporator will be changed. The boiling temperature will be changed. But in here we assume, since the concentration is only changed from 1.5% into 4%, then we assume that the boiling point of the solution is the same with the boiling point of water. Okay, next we can write down the mass balance first. For the mass balance, of course, for the feed itself, we are in here talking about the mass balance of the evaporating liquid. Yeah, F will be equal to V plus L. Yeah, and here F is equal to V plus L. And then for the component mass balance, XF times F will be equal YLV plus XLL. Since the outlet at the top of evaporator is a pure solvent, so the value of fraction of salt is 0, so we can eliminate this one, and we can just write down the information that we have. The fraction of the solid at the feed is 0.015 times the feed itself is 7,500. It will be equal to 0.04 times L, and the L itself we can find it as 2,812 kg per hour, and the V is 7,500 minus L, so the result will be 4,688 kilogram per hour. This one is the mass balance of the evaporator. To calculate the heat transfer area, we need a heat balance, where the heat balance equation, maybe you can still remember, on a heat transfer class, where 0 will be equal to F times HF minus V HV minus L XL plus UA TS minus TE. So all this information we already have it from the mass balance, right? The TS is already there, TE also already there. UA, but you need to find this, not XL, sorry, my bad. In here is HL. So where can you find the HF, HV and HF? You can find it from the steam table. The steam table itself, you can find that this one is the enthalpy of the water, so the HF, you will get it as 356 kilojoule per kilogram. The HV is 262.5 kilojoule per kilogram, and the HL is 419.2 kilojoule per kilogram. So the HV and XL, you can obtain it at the 100 degrees C, while the HF is at 85 degrees C for water. At one bar, the pressure is 1 bar. 1 bar. And from the steam table, when you use a saturated steam with a pressure of 170 kilopascal, then the temperature of the saturated steam is 115 degrees C. So this information is what we are needed in this one. So you can just enter all this known number into the previous equation, where 0 will be equal to 7,500 kilogram per hour times HF 356 minus the V is 4688 times HV this one is 267 minus 2812 times 419.2 minus a plus the UA is 2800. Well, the unit is watt per meter square Kelvin. We can convert it into joule per second. What is joule per second, right? So we have to change it into a kilojoule, so it will have the same unit with the previous calculation, joule per second. This one times A times the temperature of the steam is 115 minus temperature of the evaporator is assumed to be the same with boiling water, boiling point of a water. So from this equation, then you will get the heat transfer area is 73 meters square. So this information, you can use it to design your evaporator, and you can find the price of your evaporator from any website for plant economics. That's all for this video. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.